Hello, and we're into Unit 4, which is, we're getting towards the end of this whole thing, so we might actually make it. Um, so Unit 4 is kind of concerned with two different things. One is entropy and free energy. That's two things, but it's one thing really. Entropy and free energy are kind of one thing, and they are kind of our big idea of do chemical reactions go, right? How do we know when a chemical reaction is likely to go the direction that we want it? We've already talked about that a little bit with equilibrium constants and that kind of stuff, but we're going to move into a little bit more conceptual idea of when does a reaction actually start and move forward. And so that's what the first couple lectures here are going to talk about. And then we're going to get into an example of the types of reactions that we consider when we think about this. And we're going to look at electrochemistry and doing reductions and oxidations and other kind of stuff. So, but first we get to do kind of a little bit more kind of conceptual ideas. We're going to define entropy and free energy and then think about how does that apply to chemical reactions. All right, so the first thing we're going to do is, well, we're going to start by writing down what we're talking about. So entropy and free energy. And this first, kind of our first pass of this is going to be a lot of kind of definitions and stuff. And so there's going to be a lot of writing and not a whole lot of math or chemistry going on in this one. But if we define entropy, entropy measures at a molecular level what the possible energies of molecules are. So basically, if you have a system that has some molecules in it, what can those molecules look like, right? Can they vibrate? Can they rotate? Can they stretch out? Can they compress? Right? Are they connected to each other? Right? Is it like a solid, like crystal lattice kind of thing? Or are they kind of free flowing in kind of a gas kind of thing? So defining that and like how free are they to move around? How free are they to vibrate and move? How rotatable are their bonds? All of these things are going to come into it. And what we say, so the possible energies, when we say possible energies, what we really mean, where are we? Is microstates, right? So microstates are basically the things that I just described. And so microstates are kind of this thing, this term that we use to describe things that we can't really see and that we can't really count, right? How many ways can the molecule exist, right? And these, we're trying to measure things like vibrations, bond rotations, these kinds of things, right? So if I have a molecule, right, that's set up like this, a different microstate of this might be, oh, these atoms are a little bit closer together, or they're a little bit farther apart, or right, or they've rotated around, so this one is now pointed like this, right? All of these are kind of different microstates, and you can imagine that there's going to be billions upon billions of these things because every time you do a bond rotation, every time you do a slight vibration, that's a new microstate. And so for most molecules, there's going to be kind of an uncountable number of these. But what we do know is that the entropy, how many possible energies, how many possible energy states there are for a molecule are related to the number of microstates, right? And in fact, if we say that entropy is S, we're going to use S for entropy, right? S equals some constant, and this is the Boltzmann constant. I don't know why everything has to be a K in Gen Chem 2, but everything has to be a K, times the natural log, of the number of microstates, right? So the number of microstates is given by W, so pretend that that's a W. Now, this is not an equation that we're ever going to really plug numbers into, right? The only thing that that is important to us is that, one, we can relate the entropy of a system, the number of possible energies that are there, to the number of microstates, right? And then once we see this, we can kind of start to draw some conclusions, right? We can say things like, how does temperature affect this, right? If we increase the energy, or if we increase temperature, that means that we're increasing the energy. And therefore, if we're increasing the energy, we have to be increasing the entropy. Right? And that makes sense too. If we think about increasing the temperature, we're going to allow the molecules to vibrate more, right? They're going to have more energy in them, they're going to vibrate more, they're going to rotate those bonds more, all that other kind of stuff. And so the microstates will go up and the entropy will go up. Phases of matter, right? The phases of matter are going to affect the entropy. The fewer intermolecular forces we have, you forgot about intermolecular forces, didn't you? They're back, right? So fewer intermolecular forces as we go from solid to liquid to gas, the intermolecular forces get weaker and weaker, right? So that's the only thing you need to remember in this case. Fewer intermolecular forces, oh, for the love of the fewer intermolecular forces you have, of course, that means that you're going to be able to access more microstates, right? So the less you constrain your molecules by having them kind of connected to each other through these intermolecular forces, the more they're going to be able to rotate, the more they're going to be able to vibrate, and therefore we're going to get an increase in entropy, right? So as we go from solid to liquid to gas, the entropy increases. The size of our molecule, right? The more bonds we have, the more rotations there are. And so a larger molecule has more microstates and therefore will also increase entropy. Right, so here are some examples of things that affect entropy. The higher the temperature is, the more entropy we have. The phase change, right, going from solid to liquid to gas, increases entropy. And then the size of the molecule, the larger the molecule is, the more microstates we have, also increases the entropy. Now, all of that is great and well and good, but what we really want to do is how do we apply entropy to chemical reactions? And so we know that when we have a reactants, we have reactants going to products. We know that these chemical reactions take some energy, right? We talked about activation energy before, right? We've looked at reaction coordinate diagrams, all that kind of stuff, right? So this process requires energy, right? Now, if we look at the reactants, so if we measure the entropy of reactants, and compare it to the energy required for this reaction, energy requirement of the reaction, we're going to get a difference between the entropy of the reactants and the energy requirement of the reaction, right? If our potential energy, entropy is really just potential energy, right? We have all these possible energies that are there. If the amount of energy that's possible for these reactions to have is greater than the energy requirement of the reaction, we get a reaction that will start, right? So if S is greater than whatever, the energy needed for reaction, then we say that the reaction is spontaneous. Right? The reaction will start on its own. The reactants have enough energy. Right? The balance of this, the difference between entropy and the energy requirement of the reaction, energy requirement, is called free energy. Right? And it's not free energy because it doesn't cost anything. This is free energy, meaning it's energy that's available in the reactants in order for the reaction to occur. So as the reaction occurs, the free energy, right, that's what we're using to make that energy, to make that reaction occur. So if we can define entropy and we know something about our reaction, how much energy it takes for that reaction to go, and we know how to figure that out because we've done that with the Arrhenius equation before, right? We know the activation energy and how to figure that out, going back to rates and everything now. If we know entropy and we know the activation energy and the energy requirement of the reaction, we can calculate free energy. And if we know how those two things relate, we can say if there is enough entropy, if there's enough entropy to overcome the energy that's required, right? If our free energy is available, then the reaction will occur. So this is the thing that we're trying to calculate as we go through all these things. Now, we're not really going to use any of the equations that I put in here, right? Like the entropy equals the Boltzmann constant times the natural log of the number of microstates. You're never going to use that equation. But we are going to use the idea of that equation that as we increase microstates, we're increasing entropy. So if you have a reaction that's not working, one of the things you can do is heat it up because that will increase the entropy of your reactants, which will increase the available energy, which will increase the free energy until you get to a point where you have enough energy to overcome the energy requirement of the reaction. Okay, so this is just an example of how we're going to do this. We're going to get a little bit more specific. We're going to give you an actual equation that you can use in the next video where we apply now all of this with the laws of thermodynamics to a chemical reaction and figure out what exactly it is that we need to actually calculate.